Okay, so we all know what exponents mean. Hopefully. If not, go back and watch that video. So if we have any number, say 2, and 2 raised 5, which gives us 32. Yes. The reason why we write it this way is because this is the same as 2 times 2 times 2 times 2 times 2. Correct? And do we really want to write it that way? No. Because if that number gets larger, then this would be a problem. So, in general, that's the exponent, and that is what we call the base. So, our objective now is to extend this simple idea to all values of x and express it as a function. So, instead of having 5 as an exponent, I could come up with a function, and I'm going to have a base. I'll keep 2 as is. And instead of having 5, I'm going to have x there. So I could plug in any value of x, and for each value of x, I'm going to end up getting a y value. Agreed? So that is an exponential function with base 2. Does that have to be 2 or an integer? Not necessarily. I could have 0.25 raised x. Could I have a fraction inside? Well, obviously 0.25 is a fraction, so I can write it that way also. One key thing that you have to keep in mind, I always recommend my students when we deal with exponential functions, we have to make sure that we maintain parentheses well. For instance, say I've got 2 raised x. It's always better to write it as 2 raised x, and that part would indicate the exponential part. So if I have a minus 7 over there, that tells me that I have an exponential function multiplied by the number -7. And you can see that this is outside the exponential function. And you may argue, well, why shouldn't I write it this way? That would be confusing, agreed? You look at that and you'd say -72 raised x, which is why we've got to delineate the exponential part from anything else that we see. Good? Okay, so let's graph a simple exponential function. I like the number 2, so we'll just go with 2. What do you see? It's a curve that's going up, right? Do you see a negative value for y?
No.
No. So if you take a regular exponential function, it could never be negative. Now, if I subtracted 5 from that, then I'm going to get a negative number. What do I mean by that? So instead of having 2 raised x, let's say I had -10, right? So It is the same curve, but what happened?
It went down by 10.
It went down by 10. But you can clearly see when compared to the previous one and that one, regardless of what translation we make, you sort of see an asymptote, right? A horizontal asymptote. The original exponential function had a horizontal asymptote along the x-axis. Now that I've shifted it by 10 below the axis, the asymptote is going along y equals
Negative 10.
negative 10. And I could same 2 raised x, and I'm going to add 2. What do we expect to see? It'll also have an asymptote, but this time the asymptote is going to be at y equals 2. Good. So we need to retain 1. Let us have 2 raised x, and we all know what that's going to look like. Same curve. Here is a question. What would happen if I change that 2 to 3?
It'd have higher exponent.
What do you mean by that?
Like the curve would go up faster.
Right, the curve is going to go up faster, so right? So it is growing at a rapid rate. Likewise, if I change the 3 to 0.25, what do we expect to happen? It's going to grow slower. Double and negative. So, as x increases, it is going to go towards 0, but by changing to a fraction, we are starting at a higher value, but as we get closer and closer to a positive number, it decreases. Does that make sense? The reason being, if I have a quarter, and if I raise it to the power of -3, which means I'm on the left-hand side, yes, the graph, which is the same as saying 1 raised to -3 divided by 4 raised to -3. Correct? 1 raised to any power is simply 1. But if I move that to the numerator, what do you think would happen?
It would just be equal to -12.
-12.
No.
If that moves to the numerator, something tells me you didn't watch the video. Right? The exponent would become positive. 4 raised to 3 is 64, correct? Which is a large number for the time being. So I'm going to pick a number on the positive side. Let's say I pick 1. Instead of -3, x is now 1. What is 1 over 4 raised 1? 1/4. Is that number smaller than that number? So as you go toward positive infinity, things are going to get smaller and smaller and smaller. Agreed? So that's one way to get that curve. There is another way. That is 2 raised x. 2 raised negative x. Right? The behavior would still be the same. Why? Well, that's a fraction. And if I change that 1/4 to 2 raised negative x, when you plug in -3, what would we get as an exponent?
Wait, sorry, can you repeat that?
Huh?
Can you repeat that? I'm sorry.
So when I plug in x is equal to -3, what would I get?
Wouldn't it be because you already made it negative, it would turn positive?
The negative and negative would become positive, so I would have 2 raised 3, and 2 raised 3 is 8. But if I picked a positive number for x that moves past 0, and I pick 1, I get 2, right? So, negative side, you had a larger number, and as you go toward the positive side, things are going to get smaller, right? So, this is what we call growth and decay. If the power is positive, we call it growth. If the power is negative, it's decay. Good? With me? So, here is a case, a practical example, beginning with 23 grams of a radioactive element whose half-life period is 45 years. The mass Y in grams remaining after T years is given by that formula. And we want to know how much of the initial mass remains after 150 years. Do we see an exponential function? So the function that we have is y equals 23 multiplied by 1 over 2 raised t over 45. Based on what I said since the beginning of class today, do you believe that this is going to be a decay or a growth?
Okay.
This will be a decay. Even though that the two ways to recognize how something would be a decay is to look at the number that is inside the parentheses. If it is less than 1, between 0 and 1, a fraction, then it would be decay. Otherwise, it would be growth. Another way to recognize that a given exponential function is a decay is to move that 2 to the numerator, which would make it 2 raised negative 1, agreed? And I have t over 45. I could multiply those two exponents, so I would get 23 multiplied by 2 raised negative t over 45. Correct? So, first approach is to look at the number that is inside the parentheses. If it is 0, between 0 and 1, it implies decay. If you rewrite it, you can see that negative gets carried over to the exponent, and that should tell you that's a decay also. Does that make sense? Okay. So, that 23 is the initial amount that we started with. Why do we call it the initial amount? When we look at time, what would an initial time be? If you started something at 8 a.m., then t must be time. And if you have to bring it to the real number line, I could say 8 a.m. would be t equals 0, right? What would 9 a.m. be?
T equals 1
10 a.m.
equals 2.
and so forth, right? So if I plug in t equals 0, yes, 0 over 45 is 0. Any number raised to the power of 0 is
0. 1.
1. So 23 times 1, we get 23. Yes? So that 23 is what the problem says as beginning with 23 grams. So we started with 23 grams. And the problem goes on to saying that over time, that 23 grams decays, and it has a half-life period of 45 years, right? So do we know what half-life is? A half-life period is time when the actual amount becomes exactly half of what it was at the beginning. So what is half of that?
10, 11.5.
11.5. So half of 23 is 11.5. And what does the problem state? The problem tells us, well, the half-life occurred at 45 years. So for it to start at 23 and to get that value, it took a time of 45 years. With me? Yes? So this happened. Now, here is a logical question. Even before you start the problem, you could do a little bit of thinking. We want to know what happens at 150 years, right? Do you think the answer that we are about to find is it going to be greater than 11.5 or less than 11.5? Less. Because you started at 23 and things are dropping, and when t equals 150, it is going to be a small amount. So, and how do we find that?
Plug it in where t is.
Plug it in for t, so we would have y equals 23 times 2 raised negative 150 over 45. Yes? That's negative 10 over 3, 2 raised negative 3, so divide that by 8. Three point something. What did you
Oh,
get?
yeah, for 150 divided by 45.
No, the entire
Oh, the entire thing, I got 2.28.
2.28. Slight miscalculation there, but is 2.28 less than 11.5? Yes. So in a problem like this, even before you start, if you think a little, you can do process of elimination to identify the correct answer, right? So, a car sells for we can also graph this. $30,000 multiplied by 4/5 raise x. So if you hit graph, you see nothing. Why?
Because the max value is set to 10.
Because our max value is set to 10. So we've got to adjust the minimum and the maximum value. Well, the minimum would be eventually 0. Agreed. Over time, the price of the car is going to keep on decreasing. It is going to become 0. The maximum should be the initial value we started. So 30,000. Oh, sorry. X is the time. So let's just put the time to be 6 years. I don't mind the scale along the x-axis, to change any more than one single year. So I have 0, 1, 2, 3, 4, 5, 6 for the x-axis. For the y, we could say the minimum value is 0 because the price of the car is eventually going to approach 0. The maximum has to be 30,000. So I'll go a little higher than 30,000. So when you graph this, you've got to be careful. Why? The y scale is set at 1, which means it tells us that I go from 0 to 1, 1 to 2, 2 to 3, all the way up to 32,000. Do you think that would be a pretty picture? No. So maybe it would be best if I went in increments of 500, which might be better. Yes? So, as expected, we start with that initial amount of 30,000. We could go back and trace this. So, trace. So what does it say when x is 0, y is 30,000, which is our initial value. When t is equal to 1, we had a number already. What was that number? T equals 1. We could find it here too. So it's actually 1.02. We get 23,886. The correct answer was 24,000, right? And t equals 1. Do the same for t equals 2. Or 2.5. I get 16,970 and 38 cents. So the advantage of having this model is I could clearly identify the depreciated value of the car for any time t. You may say, I would like to know what would this price be a year and a half from now. I could simply plug in 1.5. Yes, year and 2 years and 4 months, I could simply do 2.25, and I can keep on plugging any value. So if I keep going, trying to get to 5. Okay, so at about 5.04, which is close to 5, the amount we have is 9737. But what is the actual value? The actual value is $9,830.40. Yes? Now, why is there a discrepancy? I'm not evaluating exactly at 5. I'm evaluating at 5.04. Good? Now, if I changed the window and put the maximum value as 20, because I could put any value for time t, and if I graph that, what is happening?
It's decreasing.
It is decreasing, and
Looks like it's
Flattening out. Looks like it's flattening out.
it's what?
Flattening out.
It's flattening out. So it is getting closer and closer to 0, but mathematically, would it ever become 0?
no.
No. It can approach 0, but definitely not exactly 0. So if someone asked you, based on this, what is a good time to get rid of this car?
Like, find the endpoint.
Okay.
Well, I mean, if you just wanted the cash immediately,
I could point better
The
than
first
that.
year.
So let me make this clear. There are several external factors that are involved, right, in
Yeah.
selling the car. Maybe you can't make the payment, you have some issue come up. But excluding all of those factors, if you want to base it just on this depreciation curve, when is a good time to say, okay, I don't want this car anymore?
I just point. Can I point at it?
The last point?
I was like, can I point at it? I can't really, like, unless you.
Oh, you have a laser pointer?
Nah, I ain't got a laser pointer. I'm just gonna point at the specific point I think would be the best point to be. So like on the 4th line, I guess it's the 4th dot. I would let it go off the 4th dot.
So right about the 4th year,
Yeah.
maybe the 5th year, the car has lost significant value. Does that make sense? So from 30,000, we dropped to 9,830. Lost significant amount of money. Which is why you should never buy a brand new car. But within a year, you lose value. Does that make sense? But still, people love cars.
wait, so what was the best point to sell it at?
The 4th year.
About 4 or 5.
Cause like you starting to see like the curve like hit that hits where it's like.
It still has some value, the 4th or the 5th year, right? Or maybe the 5th and the 6th year. It still has some value, and you can trade it in, and plug in 6 and tell me what you get.
$7,864.
So 7,864. So when you get that estimate on Kelley Blue Book and one of those, it will probably say 6,000 to 7,000 is the right value for this particular car. So at that point, if you're intent on buying a brand new car, it's best to take it then and get a good deal from the dealer and purchase a new car, right? The longer you wait, this amount is going to keep on going down at a rapid rate. Does that make sense? because it is not going to take a linear approach, rather it is going to take an exponential approach. Say if you waited until 9 years, plug in t equals 9 and tell me what you get.
4,026.
4,000. So it is rapidly decreasing, which is why a good time to change your car is about 6 years usually. Does that make sense? Okay. I think I'll stop there.